Understanding magnetic fields and the way that changing magnetic fields can induce currents is one of the most difficult portions of introductory physics. The aim of this video is to lay out all of the pertinent equations and the ways that you can apply the right-hand rule for all of these different situations. By doing this, we'll have a series of systematic rules in order to determine the direction of forces, currents, and magnetic fields. Keep watching to find out how we'll accomplish this.
Shot me like an electric eel, baby girl. Turn me on with your electric field.
The first equation that we're going to discuss is what's called the Lorentz force law. We already saw the first half of this equation early in the semester when we talked about electric fields. By including the magnetic portion, we'll have a complete equation that describes how a charged particle moves under the influence of electric and magnetic fields. The magnetic portion of the Lorentz force law says that the force due to a magnetic field acting on a charged particle is going to be equal to its charge times the velocity that it moves at crossed the magnetic field. The thing that makes this equation difficult to deal with is the introduction of the cross product. Whenever you see an equation that has a cross product in it, you need to apply the right-hand rule to determine the direction of the resultant vector after the two initial vectors are multiplied together. This is going to be the first version of the right-hand rule we'll discuss. I'm going to call this RHR1. This version of the right-hand rule says if you have some particle that's moving with some velocity in the presence of a magnetic field, you point your fingers in the direction of the velocity and then you curl them into the direction of the magnetic field. When you do this, your thumb will point in the direction of the force. Let's consider an example to see this in action. Consider a particle that's moving to the right in the presence of a magnetic field that points up. In order to find what the direction of the force is, we take our right hand and point our fingers in the direction of the force. Then we curl our fingers in the direction of the magnetic field, and our thumb is going to point in the direction of the force. In the case of this example, this says that our thumb, the direction of the force, is going to be pointing out towards you. Another version of this right-hand rule comes from considering what the force is on a current-carrying wire in the presence of a magnetic field. This equation says that the force is going to be equal to the length of the wire times the current crossed with the magnetic field. Now, when we apply the right-hand rule to this equation, it follows almost exactly the same way that it does when we apply it to the first equation. We point our fingers in the direction of the current, and then curl our fingers in the direction of the magnetic field. Our thumb is going to point in the direction of the force. Consider a length of wire that has a current that's flowing up in the presence of a magnetic field that is pointing out. In order to find the direction the force acts on this wire, we take our right hand and point it in the direction of the current. Then we can curl our fingers in the direction of the magnetic field, which is out in this case, and our thumb is going to point in the direction of the force. The next version of the right-hand rule, which we'll call RHR2, comes from considering what the magnetic field is produced by a long straight wire. The equation that accompanies this right-hand rule says that the magnetic field produced by a long current-carrying wire is going to be equal to mu naught, the permeability of free space, times I, the current flowing through the wire, divided by 2 pi times r, the distance that you are away from that wire. In order to determine the direction that this magnetic field goes, what we do is we take our right hand again and we point our thumb in the direction of the current. Our fingers will curl in the direction the magnetic field points. We can consider some current-carrying wire that has current pointing up. In that case, we have our thumb pointing in the direction of the current, and our fingers will curl in the direction of the magnetic field. By doing this, we can see on the left side of the wire, the magnetic field is going to be pointing towards you, and on the right side of the wire, the magnetic field is going to be pointing into the page. The final version of the right-hand rule comes from considering what the direction of the magnetic field is produced by the current going around a loop of wire. In this version of the right-hand rule, we take our fingers of our right hand and curl them in the direction the current goes around the loop. Then our thumb is going to point in the direction of the magnetic field. We can consider an example for this as well. If we had some current going around a loop in this direction, we would take our fingers and curl it that way, and then our thumb is going to point in the direction of the magnetic field. The right-hand rule can be one of the most challenging portions of physics to understand at an introductory level. I hope by laying out these 3 different ways of applying the right-hand rule, it helps you to understand how you can find the direction of forces, currents, and magnetic fields, and ultimately solve problems. Thanks for watching.